relationship. I showed you this equation 1214, namely that it's possible to eliminate the connection at a given point. Now, what this means is that by making this transformation, which is nonlinear, it's quadratic in x, by making that transformation is an acceleration, because uniform velocity could not be achieved if with two x's. So that's an acceleration. And what that acceleration does is it gets rid of the connection. So if the connection describes a gravitational field, then you can conclude that at any given point, a gravitational field is equivalent to an acceleration. And that's the way the equivalence principle is usually formulated, so that you can simulate a gravitational field by an accelerator. And that means that at any given point, you could not tell if you were accelerating or if you were in a gravitational field. How could you tell? Well, you'd have to look at an adjacent point, because the transformation that gets rid of the connection at one point doesn't get rid of it at the next point. And so at the next point, you would still see a gravitational field. So you don't get rid of the gravitational field everywhere, you only get rid of it at your own location. Now, I don't call that the equivalence principle, even though that's the way it's described, that gravity is equivalent to an acceleration. And the reason is, if I look at the geodesic equation, let me just write that back out a second. d2x lambda ds squared plus gamma lambda mu nu dx nu dx nu ds equals 0. If I were to put here some constant like 25, I could still get rid of that term. So it's a statement about this term alone. It's not a statement about the entire geodesic. And so it's a little bit misleading to say that that's the equivalence principle, because if I put here a number 25, or any other number you want, I could still get rid of that term at any given point. So I regard the equivalence principle not as that statement, but as the statement that the weight here has to be 1. Because if it's not 1, the sum of these two terms is not a general coordinate vector. So it's in constructing the general coordinate vector first, and then getting rid of the connection at a given point, you get the equivalence principle in the standard language. But I say no, the correct statement is that this expression is a general coordinate vector. And it has nothing to do with the equivalence principle. The equivalence principle is a consequence of the general coordinate invariance. Historically, the equivalence principle was discovered before general relativity, and so it seems to have a mind of its own. And I say that that's not the right way to look at it. The right way to look at it is general coordinate invariance, and equivalence principle is a special property of the geodesics associated with general coordinate invariance. Okay. Now, today we're going to discover some properties of curve spaces. Now, let me make first of all, let me make an immediate comment. Differential geometry was developed in the 19th century, long before general relativity. Therefore, we can discuss curve space without needing to make any reference to a dynamical equation such as the Einstein equations, because they just existed a long time before Einstein. So there has to be a different way to look at curve spaces. namely not related to dynamics, but purely related to geometry. So let's see how to do that. And the way we do it, I've got it right at the top, we do embeddings. Consider a line element. The s squared is dr squared, where have I gone? ds squared is dr squared plus r squared, I guess plus r squared d theta squared minus dz squared. And I'm going to take this as a curve space. I should perhaps have written, first of all, the ds squared is equal to dx squared plus dy squared minus dz squared. So I'm going to take Pythagoras, but with a funny sign. And we'll see why that's so significant in a moment. And I'm going to look at the surface, z squared is r squared plus 1. Z squared is r squared. I'm going to look at that constraint. I've got a three-dimensional surface, and I'm imposing a constraint on it. So 2z dz is equal to 2r dr, and therefore I can write this as dr squared plus r squared d theta squared minus dz squared, which is r squared dr squared over z squared, and that's equal to dr squared plus r squared d theta squared minus r squared dr squared over z squared, which is r squared plus 1. And you just complete the algebra, r squared plus 1 minus r squared. So you get dr squared over r squared plus 1 plus r squared d theta squared. Finally, if you calculate the r lambda mu kappa, the Riemann tensor, it's non-zero, and it's minus g mu kappa, g lambda nu, minus g mu nu, g lambda kappa. Now you can actually go ahead, you take the metric, here's this metric, GRR, so the metric is just g mu nu, it's just two-dimensional. It's 1 over r squared plus 1 and r squared. 0, 0. So that's the metric. You can calculate the connection, you can calculate the Riemann tensor, and that's what it is. Now, I happen to know the answer, and I know that that's the answer without doing the calculation, and I'll explain in a moment how I knew what the answer was. But for the moment, we just confirm that it's not equal to 0. So what it is you've got a surface, and you're on a constraint. And being on the constraint means that on the constrained surface, the geometry is not flat. This geometry is flat. This geometry is not flat because of the constraint. And this metric is called the induced metric. Because the initial metric, that was a three-dimensional one, was just 1, 0, 0, minus 1, which was flat. However, putting on the constraint is going to give me a smaller surface on which the geometry is non-trivial. Now, this particular metric I've chosen for two reasons. One is, it was the metric that was discovered in the middle of the 19th century by Gauss, Bolyai, and Lobachevsky. Independently, they weren't working together. They each stumbled across this particular metric. And this particular metric is important because it does not obey, because it does not obey Euclid's fifth axiom. Euclidean geometry had been written down by Euclid in the time of the Greeks, and one of his axioms was that if two lines intersect somewhere, they cannot be parallel. Now, turns out people tried very hard to see if they could form a geometry with only 4 of Euclid's axioms, and they never succeeded until these 3 people. And the reason that they didn't succeed is because prior to the discussion of this particular geometry, it was always the case that you had plus dz squared. In other words, if you had some space and you wanted to embed it in a larger space, you would always take the signature to be plus, 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 plus. The notion of embedding a space into what we now call the Minkowski signature did not exist until this particular work. Nobody ever thought, I mean, they had this geometry here. They have this geometry. It does not embed in a 3 space with a signature 1, 1, 1. It does not embed in x squared plus y squared plus z squared. It embeds in x squared plus y squared minus z squared. Now, what this also shows you is that having negative signature has nothing to do with relativity. It was already known 50 years before relativity. However, of course, relativity makes the negative 1 the dt squared. I mean, that's the change. But the notion that you could have a space with a signature that was not everybody positive already exists prior to the work of Einstein. So, and it's just the difference, of course, for Minkowski is simply that the minus sign is associated with the time. Okay. Now, so this shows you how to construct a geometry which is curved, which has a non-trivial Riemann tensor. That does not mean that it's a solution to any dynamical equation. This is completely geometric, nothing else. Now let's take one which is going to be a little bit more relevant. By the way, when this was first discussed, it was realized immediately that it was non-Euclidean. It's called a non-Euclidean geometry. It does not obey all the axioms of Euclid. Yes?
So the signature of plus, plus, and then minus 1, physically, what does that tell us? So I interpret like ds squared equals to dx squared dy squared. These are just coordinates that I'm looking at.
Yes.
They're orthogonal to each other.
Yes.
How is that different from, what is the minus sign? Why is it?
Okay, if you want to be very straightforward, you just replace z is iw, and then it's dx squared plus dy squared plus dw squared. And then you're back to positive signature. But what you've got is the third dimension is on the imaginary axis. Now, that is what we do in Euclidean field theory. The whole, I mean, many of you will know about the lattice QCD. It's done with a Euclidean metric, which means that it works with a pure imaginary time. And you just treat that as another real coordinate. So if you wanted to draw axes, you'd have to draw axes, for the original one, you'd have to draw axes in the complex plane. However, that's not something you haven't seen before. Because you've seen before x squared over a squared minus y squared over b squared equals 1 is a hyperboloid. So this is just a hyperboloid in one higher dimension. It's only when you try to assign a signature to it that you discover that hyperboloids have to have a relative minus sign. Now, what they're called mathematically is a space of constant negative curvature. In In other words, it's a hyperboloid with a curvature which doesn't change from one place to the other. Now, you can think of a saddle on a horse has a curvature, but it's not constant. Otherwise you wouldn't be able to use it as a saddle. So it varies from one point to the other. These are spaces with a constant negative curvature. And we'll see in a moment why that's so relevant to the universe in which we live. Okay, now let me give you a second example. Let's go now to 4 dimensions. Let's write ds squared is dx1 squared plus dx2 squared plus dx3 squared plus dx4 squared. And let me put on a constraint, x1 squared plus x2 squared plus x3 squared plus x4 squared equals a squared. So I've got a 4-dimensional flat space and I'm on a circle, a constrained circle, which means one of the degrees of freedom is constrained, and I've got a 3-dimensional surface. So let's see what it is. So we write it out. We take the derivative, x1 dx1 plus x2 dx2 plus x3 dx3 plus x4 dx4 equals 0. Just take the derivative. A squared is a constant. That's the important point. A is a constant. I mean, if we made a to be a function, then this would just be a bit more complicated. So now we can rewrite this as dx1 squared plus dx2 squared plus dx3 squared, and dx4 squared is x1 dx1 plus x2 dx2 plus x3 dx3 squared divided by x4 squared, which is a squared minus x1 squared minus x2 squared minus x3 squared. And now we can put this into polar coordinates to make it look a lot simpler. Well, dx1 squared plus dx2 squared plus dx, we know what it is. It's dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. And now this term here, if I were to, in a 3 space, write x1 squared plus x2 squared plus x3 squared equals r squared, then that's just r dr. So that's plus r squared dr squared over a squared minus r squared. And now collecting everything together, we get a squared dr squared over a squared minus r squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Okay. It's conventional to define k is 1 over a squared, and so that gives us finally dr squared over 1 minus k r squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Now, you notice that this is identical to this one, except it's in one lower dimension. But there's a key feature that's different here. This is 1 plus r squared, and this is 1 minus r squared. The minus sign is because I had plus a squared here. And this is a space of constant positive curvature. And the Riemann tensor is r mu nu sigma tau is just equal to minus k, sorry, is equal to k g mu sigma g mu tau minus g mu tau g mu sigma. That's what it is, and if I put k as minus 1, then I come back to minus 1. Now, geometrically, you can sit down and you can take this metric and you can do the calculation, and you will discover that the Riemann tensor, first of all, is non-zero. And it's non-zero because of the k. Now, what happens if we let a squared go to infinity? If a squared goes to infinity, k goes to 0, and the space becomes flat. So an infinitely large circle with an infinite radius you can treat as completely flat. Now, how did I know what the Riemann tensor should look like? These spaces are known as maximally symmetric. Why does it mean maximally symmetric? They have all the possible symmetries that you could have of mixing x with y, x with z, and y with z. There's no restriction. If I put here a factor of 2, I could mix x with y, but not mix x with z. So maximally symmetric means uniform. So everything looks here uniform, and all of the coordinates are being treated equivalently. Now, if I write it in this form, in 3 dimensions, one of the coordinates is being treated differently. However, how do I know that this is maximally symmetric? Because it comes from a 4 space where everything is treated equivalently. So when you have complete equivalence, you have the largest possible symmetry, and from that symmetry, you know that the Riemann tensor has to have this unique form, independent of what the form of the metric is. So you really would start with the symmetry, then you produce the Riemann tensor, and then you ask, well, let me find a specific metric which satisfies that rule, and that's the easiest way to do it is from the embedding. Now, there's a technical term which is called killing vectors. And they obey grad mu k nu plus grad nu k mu equals 0. Any vector that obeys that condition is called a killing vector. The rule is in an n-dimensional space, there's 1/2 there's n minus 1. It's just n minus 1. 1/2. That's the number of killing vectors. Now, if n is 2, which is what we have here, n is 2, then n minus 1 over 2 equals 1. There's just one killing vector. If n is here, 3, if n is 3, then we have 3 times 2 over 2. So there are 3 killing vectors. Got that right? No, that's not right. It's, because if n is 3, so it's 3 times 2 over 2 is 3. Yes, it's correct. But why am I thinking that, oh, well, never mind. It's 3. That's good. So these are spaces which are maximally symmetric. The maximally symmetric ones are very easy to construct because they are flat in one higher dimension. Now, you've got to be very careful. If you have a sphere, then the surface of the sphere, if this is just a football, the surface of the sphere would be 2-dimensional. The third dimension, which would be the center of the sphere, is not on the surface of the sphere. So when you have a surface, you can have a set of what you think might be a center, but it's not part of the surface. In fact, you can think of a spherical shell. The center of the spherical shell, there's nothing there. It's not a uniform shell. A uniform shell, a solid shell, is not the same as a spherical shell. A solid shell, from here, is a spherical shell in 4 dimensions. but with one constraint. So you always have to step up the dimension to see the picture. Now the rule is,
Professor, I think it should be n times n plus 1 over 2.
that's what I was beginning to think, yes. That's why I got it confused. Thank you. N times n plus 1 over 2. So it's 3 times 4 over 2 is 6. Yes. I knew the answer was 6. I couldn't see why. Thank you. Okay, so what have we got here? N times n plus 1 over 2. So that's 3. Very good. Thank you. So I knew the answer was 6. I just couldn't figure out why it was 6. Okay, now then. All of these spaces have the following feature, that if I give you any space, it doesn't matter what, in n dimensions, I can embed it in some higher space, which is flat. So I can have some huge space which is flat with constraints, would reduce me down to that curved space in the lower dimension. If the space is n dimensional, then it's n plus 1 is the higher space you have to embed in, and it's a half of that. And if that's 4, then this is 4 times 5 over 2 is 10, which means that any 4-dimensional space, it doesn't matter what, you can use any metric you want. You can find a 10-dimensional space which is flat with 6 constraints. Now, I don't know if that's anything to do with string theory being in 10 dimensions, and then you come down to 6, but it's telling you that from the 10 dimensions in string theory, you will have to find 6 constraints to get down to 4. And you will get down to 4, whatever those constraints are, will get you the metric down in the 4 dimensions. And that's called the compactification issue in string theory. Yes, sir?
Like these are just the 10 Killing vectors, right? Why, like they are 4-dimensional vectors, but there are 10 of them.
There are 4 what?
Like these vectors are 4-dimensional.
No, in 4 dimensions, there are 10 Killing vectors.
Right, yeah, but they have an index k mu, and mu runs from 0 to 3, so it's a 4-dimensional.
Yes.
So
No, not here. This is a 3-dimensional problem.
Right, yeah, but
We're going to make it into a 4-dimensional problem in a moment. Just hold on. Now, what was also pointed out was that this is a half n plus 1 is also the number of possible Killing vectors. The most number of Killing vectors a space can have is 10, a 4-dimensional space. But what are they? 6 Lorentz transformations and 4 translations. 6 plus 4 is 10. So if you are fully Lorentz invariant, you've got 6 symmetries, and if you're fully translation invariant, you've got 4 symmetries. Therefore, you have possibly 10 symmetries. Now, the more symmetry you have, the easier it is to construct the geometry. If the number of symmetries gets very high, then embedding in just one higher dimension can do the job. In other words, if a space is maximally symmetric in its own dimension, you only need to embed it in one higher dimension to construct the metric. You don't need to construct the metric to know the Riemann tensor. That's given you automatically. You only have to, if you want to find the metric, then the embedding is the easiest way to do it. Find a metric that will obey this rule. Okay. So embeddings get to be very convenient if we have a lot of symmetry. Now, where in the real world do we have a lot of symmetry? Well, let's just consider some configurations. there's something called the cosmological principle. Now, the cosmological principle is an extension of the Copernican principle. The Copernican principle is usually stated as no point in the universe is special. There's nothing special about using the sun as the center of coordinates for the solar system or using the Earth. Nowhere is special. The cosmological principle says that the universe is homogeneous and isotropic. Isotropic means rotations about a point, and homogeneous means translations. Now, your immediate reaction, which is fully justified, is to think that it must be true of space and time. And that when it's four-dimensionally, when we're in 4 dimensions and it's homogeneous and isotropic, there are 10 killing vectors. That space is called a de Sitter space. And I'll show you how to construct a de Sitter space in a moment, but it looks like this is not the universe we live in, because it seems that time is evolving differently than space. That's called the Hubble expansion. The theory that used this cosmological principle, and that one is called the perfect cosmological principle, was initiated by Hoyle, and it's called the steady state theory. Its nice feature is that it's a universe which does not have a beginning, which in a sense is rather nice, because we don't think the universe should have an end, so why should it have a beginning? I mean, if you draw a line, you can go in that direction or the other direction. There's nothing to stop you. But it turns out what would stop you is a singularity. And that singularity is called the Big Bang. However, the steady state theory has no Big Bang. And we'll see why in a moment. Now, it looks like we are only 3-dimensionally homogeneous and isotropic. Namely, the spatial sector of the universe has the structure that I just gave you over here. That means that the metric dt squared, c squared dt squared, minus, now you would put here, dr squared over 1 minus kr squared, plus r squared d theta squared, plus r squared sine squared theta d phi squared. That's the spatial piece. But if the spatial piece expands uniformly in time, the relative locations of all of the objects in space doesn't change. And so we can put here minus a squared of t, where a squared of t is the expansion radius. So it's 3-dimensionally symmetric, but not 4-dimensionally symmetric. To get it 4-dimensionally symmetric, you need 2 things. K equals 0, and a of t is e to the ht, where h is the Hubble parameter. That is a special case. This geometry here, which we just constructed, is called Robertson-Walker. It's called Robertson-Walker. And if it turns out that a of t has this very particular structure, that's a special case of Robertson-Walker, that particular structure makes the theory have higher symmetry. This is an arbitrary choice, an arbitrary a of t. Can I choose a different a? Can I find a special a of t for which I have more symmetry? And the answer is yes, and that's the exponential form, and that, of course, is the inflationary universe. The inflationary universe inflates very rapidly, it expands exponentially fast. Its whole idea is that during this period of expansion, you have a higher symmetry. You are in the perfect cosmological principle for a small amount of time. Okay. But today, we have this geometry, and one of the primary challenges of cosmology is to measure A of t and to measure k, and to have a theory that will predict those measurements. Those are the challenges, and I'm sure you all know, and we'll get to this hopefully tomorrow, currently the theory needs something called dark matter and something called dark energy to do that. And that's where the notions come from. Now, A of t, from what we can see, is that A dot is positive. That seems to be what we measure. A double dot, well, if A is e to the ht, A dot is h, e to the ht, and A double dot is h squared, e to the ht. And so A double dot would also be positive, which means the universe is accelerating. However, what we find today is that it seems only to be accelerating now, not always accelerating, which means that A of t, and let me give you what we think today, A of t is t to the 2/3, A dot is 2 over 3 t to the minus 1/3, and A double dot is minus 2 over 9 t to the minus 4 over 3. So if the expansion rate is t to the 2/3, that's the standard expansion rate, which I'll derive that probably tomorrow, but I just wanted to show you. It leads to an A dot and an A double dot, which is negative. Now, acceleration you expect to be negative because you think the universe is expanding, but objects attract and they slow down the expansion. So it was always a thought that A double dot would be negative until it was measured. And once it was measured, it was, as I'm sure you all know, with the accelerating universe, it was found to be positive. So you needed something to push this minus sign into a plus sign. And that's dark energy. That's what it will have to do. Okay. Now, these are examples of geometries which are defined by their symmetry. Now, you also see that A dot blows up at t equals 0. It becomes infinite. That's the Big Bang singularity. So I said a moment ago, we can go forward in time, but can we go backwards in time forever? Well, yes. If it's e to the ht, we can go through t equals 0 and go all the way to t equals minus infinity. And that function never blows up. Whereas this one, if we start going backwards, it does blow up. So the notion of a Big Bang is the notion that as we go back in time, we will encounter a singularity. If we don't encounter a singularity, then in principle we can go back forever. And so that's basically the origin of the Big Bang theory. Historically, Friedmann solved the Einstein equations, found this solution, found that A of t growing like a power as a property of the Einstein equations. Subsequently, Robertson and Walker pointed out you don't need a dynamical equation. You can get it from the geometry alone. but then you don't know A of t or k. So what are the options for k? Well, we saw we could have minus, negative curvature. We saw we could have positive curvature. And of course, we could have 0. So what are the options for the universe? It could be a plane, it could be a sphere, or it could be a hyperboloid. Now, if it's a sphere, which is the easiest thing to picture, you can ask me, where is the center of the universe? And the answer is, it's in a higher dimension. It's not on the three-dimensional surface. It's almost as though we're living on a three-dimensional sphere whose center is off in a fourth dimension. So it's an imaginary surface. And Gauss was very diligent in pointing out you can discuss a surface within itself. You don't have to think of it in terms of an embedding. And of course, for the universe itself, we can't do an embedding. Because if it was embedded in something bigger, that would be the universe. Unless it's an imaginary, fictitious embedding. But then we can only use it as a mathematical tool to construct a geometry. Okay. Now Gauss, Bolyai and Lobachevsky discovered that metric in 15.2. It was a two-dimensional metric. One second. And they asked, Gauss gave Riemann, his grad student, the challenge to generalize it to n. And the generalization is the Riemann tensor. Yes?
If you're talking about an imaginary embedding in a higher dimension, does that have to do with the minus sign appearing?
Either way.
As you explained it.
No. The Gauss one had a minus sign, but this one has a positive sign. The embedding, if I had embedded this in a sphere, if I had made that minus, I would have embedded it in a high dimensional hyperboloid. They're both fine. You see, in the end, what matters is what's the signature of the space. But when I gave you the rule that you could always embed in nm plus 1 over 2 dimensions, it's true for any signature. Now, what happens in string theory is the signature of string theory is 9 plus 1. 1 time and 9 space. They compactify down to 3 plus 1. In other words, they get rid of 6 spatial dimensions. They don't get rid, it's not 8 plus 2 or 7 plus 3. We don't really know what to do when there are 2 times. But having said that, I should tell you that the conformal group embeds in a space with two times, 042. And ADS5, which is part of ADS5 CFT, again embeds in a space with 2 times. Okay. Now, so we can get a long way on discussing the geometries without making reference to equations of motion. The Einstein theory, which we'll get to in a few moments, was a way of giving you a set of dynamics that would actually relate A or K to the matter content of the universe. And we'll see how that works in a moment. But there's one other metric I want to introduce you to, and that's called the Schwarzschild metric. Now the Schwarzschild metric is not homogeneous, it's only isotropic. Namely, what it is you have a star at rest and you're spherically symmetric about the star. The Newtonian potential only depends on the radius, so you have spherical symmetry, but only about one point. If you had a whole universe of stars and every one of them was isotropic, the whole thing would be homogeneous. But just a single star on its own, and you would guess immediately, you will have fewer killing vectors. In fact, there are only 3. The metric is ds squared is c squared dt squared times 1 minus 2mg over c squared r minus dr squared over 1 minus 2mg over c squared r minus r squared d theta squared. That is the Schwarzschild metric. Now, you immediately notice that there's a term here in the denominator. Well, that's not new. We already had a term in the denominator here. And what happens if r is equal to 2mg over c squared? What happens at that point? This becomes infinite. That's the black hole. So a black hole is a singularity in the Schwarzschild metric. The Big Bang is a singularity in the expansion radius. But they're basically the same. One is a spatial and the other is a time, but they're basically the same. Now, just so that you will, it's pretty clear that we're not inside a black hole, that the sun is not a black hole. So you calculate this number, and the Schwarzschild radius of the sun is, if you put in the numbers, it's 10 to the 5 centimeters. Fortunately, the radius of the sun is 10 to the 11 centimeters. So the Schwarzschild radius occurs deep inside the sun. So this is not of concern. The concern would be if the radius of the Schwarzschild radius was of the same size as the physical radius of the material in the star. That becomes a black hole. So what will happen is, if the sun were to collapse down to 10 to the 5 centimeters, it would become a black hole under its own gravitational attraction. Okay. So this is the Schwarzschild metric, and the interesting thing is, Einstein never derived this. You would think he was doing the solar system. The first thing you do is you've got the Einstein equations, get the geometry outside the sun. But the geometry outside the sun is weak. So Einstein was able to solve the problem perturbatively. It would appear that he was not aware that there was an exact all-order solution. I don't know whether he didn't look for one, but he didn't need to look for one because the modification of the orbit of Mercury was 1 part in 10 to the 8, so you didn't need to go very far. However, Schwarzschild, maybe a year or two later, solved the Einstein equations exactly and got the Schwarzschild solution. And he discovered there was a singularity. And while everybody is gung-ho on black holes, there was one person who wasn't, and that was Einstein. He did not like the idea that his equations gave singularities. And he spent a lot of time trying to construct solutions to the Einstein equations without singularities. But it seems that the evidence is already there. Okay, now in order to construct the Einstein equations, we've introduced the Riemann tensor. I want to write the Riemann tensor in a slightly different form. It's a bit awkward to have the indices r upper lambda, lower mu lambda, lower mu nu kappa. So I'll bring everybody down by just writing that is equal to g sigma lambda r lambda mu nu kappa. I can just lower one index using the metric, and that turns out to be 1/2 d2 g lambda nu dx kappa dx mu minus d2 g mu nu dx kappa dx lambda minus d2 g lambda kappa dx nu dx mu plus d2 g mu kappa dx nu dx lambda, and then plus g eta sigma gamma eta mu lambda gamma sigma mu kappa minus gamma eta kappa lambda gamma sigma mu. Okay. Now, this structure, all four indices are being treated the same way, and then you can check the symmetry. What happens? What's the relation of lambda mu to mu lambda? You can just read it off from here. So you can find that there are these symmetries. R lambda mu nu kappa is equal to R nu kappa lambda mu. Then there's an anti-symmetry. R lambda mu nu kappa is equal to minus R mu lambda mu kappa. I think it is, which is equal to minus R mu, and then I can swap R lambda mu, but I can swap the other two, so that becomes kappa nu, and then this is equal to R mu lambda kappa nu. You just look at this expression, and it's very easy to read these off. And then finally, there's a cyclic condition, R lambda mu nu kappa plus R lambda kappa mu nu plus R lambda nu kappa mu. Let me see. Mu nu kappa lambda kappa mu nu lambda mu kappa mu equals 0. So it's cyclic on the last three indices. Okay. That is good news. Because if we just look at the Riemann tensor in 4 dimensions, in principle, lambda can go from 0, 1, 2, 3, it has 4. 4 times 4 times 4 times 4 is 16 cubed, is 256. So it could have 256 components, and we'd still be calculating. But it turns out these conditions reduce it down to 20. There are only 20, and the proof is here. This is standard proof. The only thing you need to know for this talk is that there are only 20. But there's more. There's more. For those of you that are aware of of the conformal gravity theory that I work in, let me just mention that from the Riemann tensor, you can construct the Ricci tensor and then the Ricci scalar, and you can construct this peculiar combination in 17.5. That's called the Weil tensor. The Weil tensor is the traceless piece of the Riemann tensor. And what is happening is the Riemann tensor has 20 components. The Ricci tensor only has 10 because it's 4 times 5 over 2. It's only got 10 components. It's symmetric. So what happens is 20 is equal to 10 plus 10. So you can describe the Riemann tensor in terms of components, 10 of which are the Ricci tensor, and the other 10 of which are the Weil tensor. In the standard theory, in standard gravity, the Ricci tensor describes the dynamics, the Einstein equations. The Weil tensor describes a gravitational wave. And this is a very nice partition between dynamics and gravitation, that produces a gravitational wave and then the propagation of a gravitation. So However, what caught my attention, which is far more important, is that if you take a change on the phase of the Weil tensor, it goes into itself, even though these functions, sorry, if I make a change in the metric, even though when I change the metric by a phase, and there are derivatives of alpha which will occur, and they will occur in the Riemann tensor, the Weil tensor is the object for which all those derivatives drop out. Just like the gauge, like f mu nu is independent of the gauge transformation. It also has a second property, that if the Weil tensor vanishes, the geometry is conformal to flat. And let me just show you again. So the Weil tensor is, the Weil tensor transforms without any derivatives, but I can also transform the geometry by changing the time to conformal time to a function of time times something which is a flat metric. So the nice feature is that the Weil tensor vanishes if the geometry is conformal to flat. But we just saw a moment ago that the Robertson-Walker geometry is conformal to flat. Therefore, standard cosmology can be described by maximal symmetry or by vanishing Weil tensor. They're equivalent descriptions. Now, but that's only an aside. Now, we've seen the Riemann tensor. Now I want to do something. Now, what I want to do is I want to do the trick that we did before of going to a coordinate system where I can get rid of the gamma. We just did that a moment ago at the beginning of the lecture. When I do that, at that point, I get 18.1. So now, the grad eta of r lambda mu nu kappa is now an ordinary derivative, d by dx eta, of whatever that ghastly thing was. There was a 1/2 d2 g lambda nu dx kappa dx mu minus d2 g mu nu dx kappa dx lambda minus d2 g lambda kappa dx nu dx kappa plus d2 g mu kappa dx nu dx lambda. That's what we had. And then we had plus two gamma terms, gamma gamma minus gamma gamma. And we would take the gradient of that as well. So that's still an identity. But now I work at a special point where the gamma vanishes, the way I just showed you before. So we can throw that away. And now we can start manipulating this as an ordinary derivative. And ordinary derivatives are very easy to handle. And you can show that d eta r lambda mu nu kappa plus d kappa r lambda mu eta nu plus d nu r lambda mu kappa eta is equal to 0. You can show that directly, you just add up all the derivatives. They're very straightforward. Because each term is three derivatives and the setup to do this. Now, that is true at this special point. Therefore, I can covariantize the theory to any point, and therefore I can now write these as grad eta r lambda mu kappa plus grad kappa r lambda mu eta nu plus grad nu r lambda mu kappa eta equals 0. So I can now do that. Now, this is called, I'm just covariantizing. Having got that expression, I now multiply by g lambda nu. So when I multiply by g lambda nu, I get grad eta. Lambda nu is called r mu kappa. That's the definition of the Ricci tensor. It's the lambda nu contraction of the Riemann tensor. Now I've got a lambda here and a nu there, but I need the lambda to be 1 and 3. So I have to swap over the eta and the nu, but they were antisymmetric, so that becomes minus grad kappa r lambda r mu eta. And then the last one is, this one I can't do anything with yet, plus grad nu r lambda mu kappa eta equals 0. But I still have got the Riemann tensor. So I'm going to have to do another contraction. So the next contraction that I do is I now multiply by mu kappa. So let me just remind you, g lambda nu r lambda mu nu kappa is called r mu kappa, and g mu kappa, r mu kappa, is called the Ricci scalar r. So I'm now contract with mu kappa, so I get grad eta times r minus grad kappa r kappa eta, because the g mu kappa will raise that index, and then here the mu kappa is going to be minus grad nu r lambda eta equals 0, because I have to swap over the kappa with the eta to get them in the right place, but that gives me a minus sign because it was antisymmetric, and now I get that expression. Okay. However, that expression, if I got it right, grad eta r minus grad kappa r kappa eta minus grad nu r nu eta, except I hadn't, oh, I should have moved the nu upstairs when I contracted those, I'm sorry. And now you can combine those into the following relation. Grad mu r mu nu minus a half g mu nu r. And we just take this. The first term is grad mu r mu nu. That's this term. That term again. And then that's g mu nu. That's just grad nu times r. So we can write this out. This is grad mu r mu nu minus a half grad nu r equals 0. So let me multiply it by 2. So I have the grad here and the grad there, and there's the gradient of the r. That relationship is called the Bianchi identity. So what it tells us is there exists a geometric object which has two indices, which is covariantly conserved. Now this is initially a bit of a surprise. Now let me explain what the surprise is. There were three possible choices for a second order derivative equation. One would have been r mu nu itself. The second would be r mu nu minus a quarter g mu nu r. And the third would be r mu nu minus a half g mu nu r. Now what is special about this one? This one, the trace is r. The trace of g is 4. 4 over 4 is 1 minus r. That one is traceless. This one is covariantly conserved. This quantity is known as the Einstein tensor, G mu nu. And this one is covariantly conserved. Now, this one is traceless, this one is covariantly conserved. Now the question is, which one is the better one to use? Well, the energy momentum tensor of electromagnetism is both traceless and conserved. So you still have a choice. But the energy momentum tensor of ordinary matter is not traceless, it's only conserved. And so Einstein in the end settled on the Einstein equations to be R mu nu minus a half G mu nu R is proportional to the energy momentum tensor, because the energy momentum tensor is conserved, that's always been true, and the coefficient is minus 8 pi g. And those are the Einstein equations. So to get the Einstein equations, the key thing that we had to do was recognize that while the Riemann tensor is the measure of curved space, the Riemann tensor's got too many indices. It's got 4 indices. Whereas the source of gravity, which is going to be some mass, which is going to produce a geometric effect, the energy momentum tensor only has 2 components. Only has 2 components. Therefore, we need some 2-component object, and that 2-component object is the Ricci tensor. But then, what do? Do we take the Ricci tensor, the traceless piece of it, or the covariant, or one which has a 0 covariant derivative? And the answer is, because we're looking to generalize del squared phi equals rho, the del squared phi is going to be related to a second derivative of the potential, and the rho is going to be related to the energy momentum tensor. Therefore, we need something which has 2 indices. But that means there are 10 equations, but that's okay, because there are 10 G mu nus. And that's just the right number of equations. Now, these then are called the Einstein equations. Now let me just mention to you that if you take an action, d4x g to the half times the Ricci scalar, sometimes I write it as r, and sometimes I write it as r alpha alpha, where I summed over alpha. I mean, either notation is fine. If I take this action, the action of gravity must be a general coordinate scalar. Now what do we know? We know that g to the half has to be there to make the d4x be general coordinate invariant. That's the measure, that's the Jacobian. And then it has to be a general coordinate scalar. The only scalar we can build out of the Riemann tensor is the Ricci scalar. Now, if you do a functional variation of the action with respect to the metric, you get R mu nu minus a half G mu nu. In other words, the quantity that is favored is always the Einstein tensor. And what a functional variation means is you want to go between 2 points. You ask, what is the best path to get between the 2 points? Now, you know, if you have a field, and you have a gate there and a gate there, you will see that that path will be trodden over the generations by many people. It's the geodesic. It's the shortest distance between the 2 points. Almost everyone on this planet knows how to figure out how to get from one corner of a field to the other without knowing what a geodesic is. You just know from daily experience. But now you could have asked, well, how do you know that? Well, you try that one, you try that one. Which is the one that works best? It's a generalization of Fermat's principle that light takes the the minimum time to get from point A to point B, and so on. Now, let me just tell you about Fermat's principle. You can say the following: we have a light signal, we want to get to there, we go this way, and then you show that the angle of incidence equals the angle of reflection. That's Fermat's principle, which I'm sure you all know. But it's very, very mysterious, because it's not saying that you tried all of these different possibilities and found the one that was the shortest. What it's saying is the source emits light in every direction, but you want to get to a particular point, not to an arbitrary point. To get to a particular point, the light that did go that way took the minimum time between the starting point and the end point. It's not as though you sampled them. If you asked it to go to some other point, it would have taken a different minimal time. But it always takes the minimal time. So it's not as though, I mean, this was always regarded as somewhat mystical. How does the source know ahead of time where it's supposed to land? And the answer is it doesn't, because it sends signals in every direction. Yes, sir?
Is there a sensible way to construct a functional from which we would get, like, for example, the trace-free version?
Yes. Okay. You can't get the trace. When you vary this with respect to the metric, you're necessarily going to, there's actually a rule. The variation of the action with respect to the metric is covariantly conserved. That's a general rule, which is why the Einstein tensor is covariantly conserved. You can never get something which is not covariantly conserved by varying with respect to the metric.
Okay, so if we want a functional description, it
okay,
necessarily means.
Okay, so I don't know of any functional description that will get you a variation that will give you the trace.
Okay.
But what I do know is that in the conformal gravity theory, you get a function which is both covariantly conserved and traceless, which is why I like it very much. To me, it was always very puzzling. Why would we bypass this? And the answer is we can't. We have no choice in principle unless we chose a different I. Could we find an I for which it was covariantly conserved and traceless? And the answer is yes. And that's the one based on the Weil tensor. So why would I want to do that? Because we've agreed we need 10 components. We have 10 components in R mu nu, but we've got another 10 components in the Weil tensor. 50-50. Or 10,000 to 1, if you read the literature.
But in a second derivative theory, that's the only possible one, I guess.
I'm sorry? Yeah.
Like in a second derivative theory, that's the only possible one.
For the Ricci scalar, that's the only possibility, yes. Yes. The quantity that, since you asked me, I is equal to the integral d4x g to the half r mu nu minus a third r squared. That particular action is locally conformal invariant. Its variation gives you a tensor which is both covariantly conserved and traceless. Yes. Okay. Now we'll introduce the energy momentum tensor. I think I have a bit of time to show you what that is. So those are the Einstein equations. So the first remark is, oh, by the way, I should have said the nice thing about the functional variation is that you show immediately that the Einstein tensor is covariantly conserved. What I did before was I used this explicit form in terms of the Riemann tensor, manipulated all the indices, did some derivatives, and showed you that we had the Bianchi identity. What the nice thing about the functional approach is that you never need to know anything the functional variation will give you the answer. Now, maybe I should just explain what functional variation is. Suppose I have some path, x of t, is the sum on an t to the n. I don't yet know what it is. That's an arbitrary path. Ordinary derivatives, you vary t. You get x dot, x double dot, and so on. Functional variation is you vary an. In other words, a functional variation is you vary how x depends on t. Not how it changes when you change t. For a fixed t, how does it depend on t? And those are the different paths. And so you can label all of the paths between the two endpoints by different combinations of an. Now, I'll also tell you one other thing. What Friedmann discovered was that if you do the functional variation of some general action and you get the minimum, the particular choice of the an for which the answer follows, then you integrate back over all of those an. That's called the path integral. And that gives you the quantum theory. So the variation of an action to get the minimum is classical mechanics. The integration back up over all of those exact self-same paths gives you the quantum mechanics. And what is the quantum mechanics? What are these other paths? These other paths play no role in classical mechanics. So in classical mechanics, this is a mathematical convenience, because you only have the stationary solution. But in quantum mechanics, a wave packet spreads. What it spreads into is the non-stationary paths. So putting them back in puts in the quantum mechanics. And that's the Feynman path integral approach, which is heavily used in things like lattice QCD. That's one of the techniques. Okay. But we don't need a functional variation today. What we need to do is to construct an energy momentum tensor. Now, an energy momentum tensor, there are two features to it. If we have a Lagrangian, I'll just do regular Lagrangian. The Lagrangian is equal to, the action is equal to the integral d for x. The Lagrangian is a function of a field and its derivative. That's a standard Lagrangian that you deal with in classical, in quantum field theory. The energy momentum tensor, d mu nu, is equal to minus d mu phi dl d nu phi plus eta mu nu times L. This is the variation of the action with respect to the energy momentum tensor. With respect to the metric, gives you the energy momentum tensor. The general definition of energy momentum tensor is variation with respect to the metric. Now, why is that so important? Because the Einstein tensor is also variation with respect to the metric. So if I have action 1 plus action 2, variation with respect to the metric will give me Einstein tensor equals energy momentum tensor. Couldn't give me anything else, because they're derived the same way. Now, you will find in classical mechanics that the energy momentum tensor is never determined this way. There's something you call the canonical energy momentum tensor, which you construct by inspection. But let us see what happens here. We have the Euler-Lagrange equation, d mu, the variation of the Lagrangian with respect to d mu phi, minus dl d phi is 0. Those are the equations of motion. That's standard classical mechanics. So let's calculate the derivative of the energy momentum tensor. It's minus box phi dl d mu phi minus d mu phi d mu dl d nu phi, and then the eta mu nu gives me plus d nu times L. Now I've got something here I want. Let me see if I get it right. Mu nu, I should have taken the derivative with respect to nu. Let me go back a second. So it's minus d mu d nu phi, dl d nu phi, minus d mu d nu dl d phi plus d nu L. But the reason I did that is because I have, this one is given me by the Euler-Lagrange. So this becomes minus d mu d nu phi dl d nu phi. But this is now minus d mu phi, and d nu dl d nu phi is dl d phi. And now we've got d nu of L. But L is a function of phi and d mu phi. So this is equal to plus dl d nu dl d phi d nu phi plus dl d mu phi d nu d mu phi. And if I didn't make a mistake, dl d nu phi d mu d nu phi, they cancel, and that's dl d phi d nu phi, they cancel, and that one is 0. So what we discover is the energy momentum tensor defined as the variation of the action with respect to the metric is conserved in the solution to the equation of motion. Now that's a bit of a jump, because the Einstein tensor was conserved even without imposing an equation of motion. It's conserved on every path, on every variational path. Whereas the energy momentum tensor is only conserved on the stationary path. Now, that so intrigued Einstein that he tried very hard to obtain energy momentum conservation from the fact that you couple to gravity. Now, he studied what was called the two-body problem, and basically did not succeed. And the reason is, it's because the conservation of the energy momentum tensor is not sufficient information. But nonetheless, he tried all sorts of different ways. Now, so that's the energy momentum tensor, and its great achievement is that it is conserved in the solutions to the equations of motion. Now, the next thing we have to do is, well, let's construct the energy momentum tensor of some system. And you'll see in a moment how we can do this. So now, we want to construct the energy momentum tensor in a specific situation. Okay. So let me take a slightly more complicated case. Okay. Well, let me just show you what it is. The Lagrangian is minus a half d mu phi minus a half m squared c squared phi squared. That's just a free scalar field with a mass, kinetic energy plus a mass. You calculate the energy momentum tensor, and you get, plug in the numbers. T mu nu is d nu phi minus eta mu nu 1/2 d kappa phi plus a half m squared c squared phi squared. So let me see, where did this come from? We've got over here two pieces, eta mu nu times the Lagrangian. So there's eta mu nu, there's the Lagrangian, what we had a moment ago, and the other term is d mu phi dl d nu phi, but dl d nu phi is just d nu phi. So this is the energy momentum tensor. And now let's calculate T00. It's phi dot squared minus, or I wanted to have it minus. Yes, minus, now eta 0, 0 is minus 1. And this is equal to, that's down, that's up, so that's minus a half phi dot squared plus a half m squared c squared phi squared. And that's 3 minuses, so this becomes a half phi dot squared plus a half m squared c squared phi squared. Just doing the algebra. I'll give you this as a challenge problem in the tutorial. And what is this? That's the kinetic energy, and that's the potential energy. So by taking this simple example, we find that the energy momentum tensor is nothing more than what it should be. It's the energy kinetic plus the energy of potential, which is what an energy is. That means a Lagrangian is always kinetic energy minus potential energy by the same token. Okay. Now, let me go a stage further and take a slightly more complicated case. And you'll see why in a moment. But this, I just wanted to show you that the energy momentum tensor is this function. And now you can guess that for a source at rest, this is going to be the rest energy. And so when we want to solve the Einstein equations for a source at rest, we will look to have something for which the source at rest has the energy mc squared. And you can see immediately where this is coming from. Okay. I'm now going to take this thing a little bit more complicated. You'll see why in a moment. I'm going to take that to be complex phi star phi. The equation of motion is the variation of, that's the Lagrangian, the action is d4x times the Lagrangian is equal to the integral d4x. The equation of motion is the variation of the action with respect to the field. And that is equal to box phi star minus m squared c squared phi. We take the variation with respect to phi, so that would be phi star. So that's the energy momentum tensor. The solution is, and the other one, di d phi star, is just box phi minus m squared c squared phi. So the solution here is phi star is e to the I k dot x, e to the minus I k dot x plus omega I k t, and phi is equal to e to the I k dot x minus I omega kt, where omega k is the square root of k squared. Okay. So this is just the scalar field wave equation. Those are the simple plane wave solutions. Now, why this is so interesting is I want to calculate the energy momentum tensor. Now, if I plug that into here, because this is quadratic in phi, I can write, I should have written this slightly more generally. The sum on, this should be the sum on that times a coefficient ak, and that should be the sum on that times a coefficient ak star, because all the momentum solutions are solutions to the equation. So if I were to insert this in here, I would get cross terms between one ak and another ak star. It would not be diagonal. Now, so that's the solution. If you take the general solution, which is an infinite sum of plane waves, and an infinite sum of plane waves, and you put them in the energy momentum tensor, you're going to get a double sum of plane waves. And now comes the perfect fluid approximation. The perfect fluid approximation is to add incoherently. Now what does that mean? If I take the modulus of A1 plus A2, modulus squared, I get mod A1 squared plus mod A2 squared plus twice A1 star A2. And this is how, if you add two wave functions together and you take the modulus squared to get the probability, there's always going to be this interference term.
But
That is, yes?
so would there also be a cos theta?
What is that?
Like the angle between the two waves?
No, these are just any two functions. Any two A1 and A2. Did I follow your question?
Yeah.
Okay. These are arbitrary A1 and A2. So if I just take modulus squared, I'm going to get a cross term. That's called coherent. Incoherent is you ignore the cross term. Now, why could I possibly ignore the cross term? We train you very hard in quantum mechanics to tell you that the cross term has all the physics in it. So why can we ignore it? Because this is a statistical problem. And what happens is, if you have a theory of particles interacting with each other, the energy will depend on the kinetic energy and the potential energy of interaction. But when you get thermal equilibrium, you get the Maxwell-Boltzmann distribution, and the Maxwell-Boltzmann distribution f of v is e to the minus a half mv squared over kt. You all know the Maxwell-Boltzmann distribution. It doesn't depend on the scattering. It doesn't depend on the potential. The Maxwell-Boltzmann distribution is independent of the potential. Now, how can that be? What happens is the Boltzmann equation relates a derivative of the distribution function to a scattering cross-section of particles scattering and scattering in and out. And that never goes away. The Maxwell-Boltzmann solution is the derivative vanishes and the scattering term also vanishes. It's a solution which makes both sides vanish. And the way that it makes both sides vanish is the particles are still interacting with each other, but any time a particle is knocked out of a particular point in phase space, another particle is knocked in. And so thermal equilibrium does not mean rest, does not mean that nothing's moving. What it means is that phase space has arranged itself through thermalization, that any time a particle enters a region of phase space, another particle leaves, such that the distribution doesn't change. In other words, the scattering cross-section is needed in order to maintain equilibrium. But the equilibrium that it maintains is independent of the cross-section. To me, that's the most remarkable aspect of the Boltzmann equation. That without interactions, you can't reach thermal equilibrium, but when you do, it doesn't depend on what the interactions were. Because the interactions will now constantly knock the particles back into the same place in phase space that they just were. This is what Boltzmann called molecular chaos. Now, what that is telling you is I could have constructed the distribution function by pretending that I had a set of free particles with no interactions whatsoever. That's the incoherent. So perfect fluids reach thermal equilibrium, and in the thermal equilibrium you can treat each particle as acting independently. They're no longer scattering. You can pretend that they're not scattering against each other. Not that they're not, but that it doesn't modify the dynamics. So a perfect fluid is simply an ensemble of particles which are you no longer need to add them coherently. So let us see what that buys us. So now, when I plug these solutions into the energy momentum tensor, I find AK star is equal to velocity of light divided by V times omega k, that's the normalization, and T mu nu is just equal to C over V, K nu over omega k, where K mu is equal to omega k, and then the vector k, because it's a 4 vector. Now, that is what I get if I don't have any AM prime star contribution. That's the incoherent summation. And so we have all of these modes, and now we have to sum over all the modes. So let's do something. Let's take a simple mode. So the first mode will just be K mu is equal to omega k over c, and then it's propagating in the z direction, 0, 0, k. And we evaluate it, and we get T mu nu of kz for this particular expression is omega k over c times the volume, 0, 0, k over v, 0, 0, 0, 0, 0, 0, 0, 0, and then k over v, 0, 0, c k squared over v. We just evaluate it, because the k is in the z direction, so the only terms that appear are 0 and 3, and 3 and 0. Nothing else appears. Okay. Now, we're going to take a second one, which is k mu is in the opposite direction, omega k over c, 0, 0, minus k. And when I do that, I'll get T mu nu of minus k is equal to omega k over cv, 0, 0, minus k over v, 0, 0, 0, 0, 0, 0, 0, 0, and then lastly, minus k over v, 0, 0, and the last one is the same, c k squared over omega k v. I've calculated the energy momentum tensor for a mode propagating in the z direction, and a second one for a mode propagating in the opposite direction. Now I'm going to add them incoherently. So instead of adding the wave functions, I add the energy momentum tensors. When I add them incoherently, I get T mu nu kz plus T mu nu minus kz, add them up together, and you see something remarkably nice happens. 2 omega k over cv, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and the last one is 2 c k squared, I think it is, over omega k. So when I add them incoherently, I get rid of the off-diagonal terms. Finally, the rest is straightforward. So now I have to add on the same thing for mode going in the x direction, the y direction, and the z direction. And you can see immediately what's going to happen. So T mu nu of kz plus T mu nu of minus kz plus T mu nu of kx plus T mu nu of minus kx plus T mu nu of ky plus T mu nu of minus ky is equal to the same thing, 6 omega k over CV, 0, 0, 0, 0, then that's 2c k squared over omega kv, 0, 0, 0, 0, 2c k squared over omega kv, 0, and finally 0, 0, 0, 2 omega c k squared over omega kv. And this is now completely diagonal. The 3 diagonal elements are all equal, the spatial piece, and this is usually written as rho 0, 0, 0, 0, 0, pressure P 0, 0, 0, 0, P 0, 0, 0, 0, P. It has T0, 0 is the energy rho, the density, energy density, and each of these diagonal terms is the pressure. We introduce a vector u mu, which is 1, 0, 0, 0, and then T mu nu is rho plus P u mu u nu plus P, in this case, eta mu nu. Let's just see why. If I take T0, 0, that's going to be rho plus P. Eta 0, 0 is minus 1. Rho plus P minus P is rho. If I take mu and z to be spatial, then they're 0, and that's just P times 1. So we can write this in a covariant form by doing this analysis, and therefore we can now generalize it to curve space. So what we discover is the perfect fluid, which you'll find in all the textbooks, it starts on page 1, this is the perfect fluid. Actually, the way that it's constructed is by an incoherent averaging over all of the modes propagating in the system, and if they're propagating in a curve space, then you write the covariant generalization. But either way, you finish up with the Einstein equations in the end. R mu nu minus a half G mu nu R. It's got to be something to do with T mu nu. The dimensions have to be that you put in Newton's constant, because they have different dimension. It's conventional to call it A pi, and it's a minus sign only because I work in a metric in which eta 0, 0 is minus 1. So the Einstein equations now, we understand what they are. The Einstein tensor is the one that's covariantly conserved by construction. The energy momentum tensor will typically be a system in which we have incoherently averaged over all possible modes of the system. And the more interesting case, of course, is when the modes are propagating in the geometry, we almost have an impossible solution, a system. However, if we assume the geometry and then let the modes propagate in that geometry, those equations will then fix A of t and k. And that's a calculation I myself did with Dimos Kazanis in 1988, I think, long time ago. Okay, but this, otherwise, in general, if you didn't know the metric and you wanted to solve these equations exactly, you would have to take the wave equation, get the modes in the wave equation, average them incoherently into the metric, and find the metric that satisfies that system. As far as I know, nobody's ever done that. I've done it for Robertson Walker. I have not seen it done in any other place. What you do instead is you bury all the information in rho and p, without ever asking, how did I make this rho? What were all the modes that went into it? Okay. Now it turns out that in Robertson Walker, the symmetry is so high that you are actually able to do what I just said without needing to have solved the problem from the beginning. even though Dimos Kazanis and I chose to do so just to see that it worked. We were very disappointed. We were hoping that that calculation would tell us what k was. That maybe it would only work for a particular value of k. We were very disappointed because it works for all values of k. So we didn't gain anything except understanding. Okay. Now we've got the Einstein equations given in 21.4. Okay, there's a c cubed over there as well. I can tell you the following, that if you work in astronomy or gravity and you leave out factors of c, they're very easy to figure out because you're usually off by 10 to the 10. So you know you're missing a c. What is much harder, and what I had to do once, was to stop setting h bar equals 1. And to go back and put h bar in is very, very difficult. In fact, I cheated on you, because when I wrote the mass term minus a half mc squared times phi squared, there should have been an h bar squared there. That should actually be an inverse length, which is the quantum wavelength of a particle of mass m. That was the thing that you should really have had there to get the dimensions right. In fact, you can't actually write a classical equation for a field with a mass without using Planck's constant. So what's classical mechanics? Why should h bar appear in classical mechanics? Well, remember, Planck himself pointed out that the dimensions of the action was h bar. So classical mechanics is not h bar equals 0. Classical mechanics is commutators equal 0. So if I write the commutator xp is ih bar, then that goes into, of course, xp equals 0. So then the fields commute. So that you can say, well, that's because I said h bar equals 0. But that doesn't mean that h bar disappears from all of classical mechanics. The dimension of the action is Planck's quantum, the h bar. That's where he got it from. So if you want to have a mass, but all you've got is you've got d mu phi, so that's 1 over length squared, you have to have something else which is 1 over length squared. And from a massive particle, the only length you can make is the quantum wavelength, which depends explicitly on Planck's constant. But you can put it in classical mechanics, so it's just a number. The only thing in classical mechanics, the important feature is that fields commute. They're called C numbers. And quantum mechanics replaces them by Q numbers that don't commute. But that does not mean that you have banished h bar. Now, of course, you can't. I mean, h bar is non-zero in the real world. You can't set it to 0. One second. So what is the classical limit of quantum mechanics? It's not h bar equals 0. It's matrix element in an indefinite number of quanta. The macroscopic limit. Quantum mechanics goes into classical mechanics in the macroscopic limit, not in the limit h bar goes to 0. Yes, sir?
Like, is it more precise to say that the ratio of action versus h bar that goes to 0?
I'm sorry, try again.
Like action over h bar goes to 0.
Action, but you don't, because you don't let h bar go to 0 in the action. You only let h bar go to 0 to make the objects commute. So you make h bar go to 0 in the commutators. You don't make h bar go to 0 anywhere else. In fact, if I write down electromagnetism, the fine structure constant is e squared over h bar c. I don't let h bar go to 0, because that would mean that classical electrodynamics is based on infinite coupling. In other words, there are hidden dependencies on h bar in what we call classical mechanics. So the important thing for classical physics is only the commutators vanish. Now, how do you get a commutator which doesn't vanish to suddenly become one that does? The answer is it can't. But what you can do is you can take matrix elements of the commutator in states with a large number of quanta. And that's Bohr's correspondence principle. That will give you something that behaves just like the classical system. That's why Bohr introduced the correspondence principle. So it really is a large quantum limit, not a small h bar limit. And you just, that's just not the right way to say it. Okay. All right, but anyway, we've now got the Einstein equations, we've got the c cubed, and now let's do what Einstein did. Let's see how we can get the Poisson equation. So I'll just give you the result now, and since we're running out of time, we take as the metric, remember I had already said that I would already set the metric to be 1 plus h, where h would be the potential. That's how we discussed it yesterday. So now what I want to do, let me just remind you, what did we do yesterday? A quick look at gravity. The first look at gravity was, I just took here 1 minus h00, and I showed you that h00 was the potential. Now, what I didn't show you was that this had anything to do with an equation of motion. This only came from the geodesic. Now I have to show you that it comes from the Einstein equations. But to do that, I have to do a little bit more. I have to take flat space. I put in a 1 plus h where h is small, but on the spatial piece, I put in a 1 plus j where j is also small. So I'm going to take this metric with a 1 plus h and a 1 plus j, and now, because it's late, if you'll just forgive me, I'll just go on the screen. I calculate for this metric the Einstein tensor. The different components. It's a spherical symmetric system. H is, and j are only functions of the radius, rho. So j double prime plus 2 over rho j prime, and so on. The three terms, just 0, 0, r, theta, theta, and it's equal to 5 phi over sine squared theta. That is because spherically symmetric about a point has 3 killing vectors. And so there is some symmetry left. There's all the isotropies. So 3 isotropies. Okay. Now, we can write that out and calculate the Einstein tensor. Einstein did it by hand. When I was young, I did it by hand. But you are the blessed generation. You can take a software package, you stick a metric into the package, and it does the whole thing for you. It gives you the Einstein tensor, the Riemann tensor, the Ricci tensor, anything you want. These can all be done mechanically. They can all be done symbolically now. But in the old days, there were no computers. You had to do it yourself. And so obviously, only the simple cases were ever solved. But if you did this, you get this j and h. And so now we get g00, grr, and g theta theta. But now what about the source? Well, for a non-relativistic system, the pressure is negligible. Omega chi, don't forget, is the square root of m squared plus k squared. So m is very big, k is very small, and it's just rho. And p is 0. And if p is 0, then grr is 0 and g theta theta is 0. Those are the Einstein equations for 0 pressure. But for the momentum, for the energy density, g00 is 8 pi g over c to the 4 times rho. So, we can solve these equations immediately, and we see that j plus h is 0. Now we put in minus h is minus j into the top one, and we get h double prime plus 2 over rho h prime is equal to plus 8 pi g n over c to the 4 rho m. And that's the Poisson equation. That's the radial piece of del squared h. So what we've been able to do, very, very simply, is we've solved the theory and we've obtained the second order Poisson equation. So what are the Einstein equations? The Einstein equations are, write the second order Poisson equation in an accelerating coordinate system. Because if they're to be true, then it should not matter if the observer accelerates. And so the way that Einstein solves the problem, and let's see what we've got. We go in steps. What we have is Newton gives d2x dt squared is equal to F. Special relativity, d2x lambda d tau squared is equal to, we'll call it g mu, g lambda. So this is Newton's second law of motion, written relativistically. So this is slow velocities, rapid velocity, but still velocity equals constant. Finally, velocity not constant, or accelerating Newton, d2 x lambda d tau squared plus gamma lambda mu nu dx mu d tau dx nu d tau is equal to some force g lambda. So this is v very much less than c, but constant. V can go as high as c, but still constant. And this is acceleration, v dot not equal to 0. So the steps that we have, Newton goes to special relativity, as written in an accelerating coordinate system, but no gravity. Now you would have thought, and this is what people tried immediately, was that for gravity you try to find something in the g lambda. But then you'll never get the equivalence principle. You'll never be able to say that an acceleration is equivalent to a gravitational field unless gamma is the gravitational field. So you don't put it on the right side here, just the way you do the Lorentz force. You don't do that. You put it in the gamma. When you do that, you get the Einstein equations, and when you work through the Einstein equations, lo and behold, you now recover in the non-relativistic limit the second order Poisson equation for gravity. And that's why gravity is totally different. It's because this is Newton's second law of motion in a flat space, but in an accelerating coordinate system. Einstein goes further and says, I can use this same kind of equation in a gravitational field. Because a gravitational field is equivalent to an acceleration, provided I can find some object, which is the connection, which shows that an acceleration is the same as a gravitational field. And then you get the Einstein equations, and from them you get the second order Poisson equation. And just give you the solution. So del squared phi is equal to 4 pi g over c squared rho, integrate it up, and the solution is phi is minus mg over rho. However, we get a bonus, and it's the bonus that is the magical result. The bonus is this. We've now got, we get J, we get H, but we've also got J. We've also got J. So now let's see what that buys us. That relates to this term, which is the v squared over c squared correction to that term. And that H, that J, here we go, that J will then give us the perihelion of Mercury. That term here gives the correction to Newton's laws, the correction to Kepler. The v squared over c squared correction follows automatically from these same equations. So the same equation that fixes the Poisson equation in the first place simultaneously fixes the modification to the orbit compared to Kepler and compared to Newton. And when the number falls out and it comes exactly right, then Einstein knew he was on the right track. So this is what Einstein did himself, was just write the second order Poisson equation of gravity in an accelerating coordinate system and look for the v squared over c squared correction. Schwarzschild came along and did more. he showed that he could find the exact solution to all orders, and that led to this dramatic possibility of a black hole, and we'll discuss more of this tomorrow. Well, tomorrow I'll show you how we get the Schwarzschild solution. How did Schwarzschild do this? And then we'll see we'll then go on to cosmology.